This is our group's final presentation for the reverse challenge disassembly project.
Here is a file reverse challenge downloaded. Now / reverse challenge gdb reverse challenge, and now set disassembly flavor Intel, and then disassemble. Check. Here is the disassembled file, and now here's the disassembled file. You can see all the functions and all. And now let's set follow for more child, and we can add a breakpoint at, for example, at point 080489667. Here is the breakpoint added, and so this is the disassembled file. Add the architecture i386, and then after that we have to update sudo apt get update, and then after updating it we need to install the package lib6 i386, and then after that then we have to click yes, so that we have to continue, and then after that we have to, when we run the command /reverse challenge, actually there is no permission given to this command to this file. So actually before proceeding further, we just need to give the permissions. So we are using the chmod plus u plus x reverse challenge, and then when we give the permission, then after that we run this command, and that the command is successfully run, and then it says that no VM please. And also we just need to /reverse challenge. Stress, basically it is used to monitor and tamper with the interactions between the processes and the Linux kernel. Basically it includes the system calls, signal deliveries, and also modifications of the changes that are made in the process.
I start by running the program. We can see immediately it looks like it's actually detecting our virtual machine. So I'm going to open it up in IDA and have a look at what's going on there. We found that there's a piece of obfuscated code here that is being masked by a hexadecimal value here, and we're going to talk about that a little bit later, about how we found what the code actually says. But the solution we found to get around that was to set a breakpoint at the place where the XOR encryption happens, and change the value of the EAX register during one of those instructions, so that when it's searching for a string, the results will come back negative. So I'll go in and do that. Let's see, so I'll run it in the debugger. And then I'm going to set a breakpoint at the instruction where the XOR encryption is happening. That's 804, 8877. And then there we want to ignore that breakpoint at the first 15 times, and then we're going to want to set the EAX register to a different value. It doesn't really matter what it is there. And then after that we can delete that breakpoint and continue. And now when we run the program, we should be able to get around this first red pill. So we were able to get around that, but unfortunately it looks like we've run into another red pill here where it says, "You fool, nobody debug me." So it's actually detecting our debugger. We found another way to get around this one. What's happening here is at the call to the fork command, a child process is created, and the child process is able to run in the background untraced, and the child process actually detects our debugger using a ptrace command and terminates the program. So what we want to do is, at the point where the fork command is called, we're going to set the program up to follow the child instead of the parent process, and then hopefully what we should be able to do is prevent this jump from happening, so that we're able to get to the next function. So I'm going to go into my terminal and give that a try. what I'm going to do here is set a breakpoint at the place where the command is called. So that'll be now when I run it, I'm going to stop there, and then I'm going to set the follow fork mode to child. This way the process will not be able to run in the background. Now when we step to the next instruction, I'm going to want to change the value in the EX register to something other than 0 so that this jump will not happen and we'll be able to get out of the check function. So I'm going to just change it to 1. Now hopefully the jump won't happen. Alright, we're good.
So I'm going to quickly talk about the first red pill that we encountered. And that was when we ran the program, we were presented with a string that says no VM please. So somehow the malware was detecting that we were in a virtual environment when running the software, and we wanted to figure out how it's doing that. So we looked at the check function, and right away we saw there was a bunch of memory addresses, each with a assigned hexadecimal value. And we also saw that further down there was what appears to be an XOR on all of these memory addresses with a mask of 75, and it goes through a loop. So I went ahead and plugged all of those hexadecimal values into a program that will decrypt that. And I already compiled it, so I'll go ahead and run it. And we can see that the decrypted string is actually a Linux command. So it's lscpu pipe grape hypervisor, another pipe, and then some more formatting commands. And basically what this command does is it looks up the lscpu command, and it is searching for the hypervisor flag that indicates that we're in a virtual environment, and then assuming it finds it, it formats the results into the preferred string, which would be KVM.
So red pill 2 that we come across when attempting to find the password in this program is that the check function not only checks for the first red pill, which is the anti-VM code, which another one of my group members has already explained, but it also detects that the program is being run in a debugger. So it'll give you this code here after you get past the VM, which you can bypass by changing the code so that it doesn't run a Linux command to detect hypervisor. You can also, you'll then get this error, "You fool nobody, debug me," which means it's detecting that it's running in a debugger. A simple way to get past this is to go into the check function and simply change it so that instead of starting up here where it would normally start and go through, it simply just starts here and jumps straight to the end, which skips the entire check, which would also skip the VM one as well. But we figured out a different way to do that. Another way that you could stop it from detecting that it's in a debugger is getting the debugger to follow the child process that doesn't terminate afterwards, instead of following the parent process, which will continue the program running, and then you'll be able to get to the main function.
Okay, so if we look at the disassembly for the main function, we see that the first function that's called is unpack. And if we check out this function, we see that there's a bunch of memory addresses all with an assigned hexadecimal value, kind of similar to what we saw in the check function. And if we go down a little bit, we actually see that these values are also being bitwise XORed with this hexadecimal mask. So I went ahead and copied all these values, and I put it into my decryption program, and I went ahead and compiled it, and then if we run that, we get this string that says : "I love packing my code," and then a special character. And I don't think this special character is a part of this string, because it really is just this hexadecimal value of 0 being XORed with this hexadecimal value, which of course is probably not a ASCII character. So at this point, we're not really sure if this could be the password, or why this string is even being decrypted and encrypted in the first place. But we know that assuming the main function executes, this is being decrypted right away. So that's where we're at.